So I apologize, I left my phone upstairs, which meant I was in login, not happening. So we're gonna start today with some group work. And then we will move into a little bit of lecture. I do have a sample exam for you. My thought is Wednesday night, 6:30 or 6 to 7:30. Maybe doing a Thermo's taking an exam. 6:30 to maybe 8 doing a review. Would you like, please let me know in the chat if you would like it before Wednesday, because I know some of you are you've got something you're going to. So, and we can do it earlier than Wednesday. Hello, anyone there? Can you hear me? Okay, so I'm being told you want it for Wednesday. I can open it whenever you want it. That's not the problem. Trying to figure out. I'm assuming then you guys also have class on Monday, is that right? So you have class Monday night and Wednesday night.
Oh, not night.
Well, our last class is your class on Monday and Wednesday.
Oh, Ellie has a class. Ellie, do you have a class Monday night and Wednesday night? You have A people, you have stuff Wednesday night, don't you? Don't you have some seminar?
They've got their capstone project on Wednesdays.
They have capstone on Wednesdays, okay. Would you be brain dead or should we do it Tuesday right after fluids?
I mean, hell.
I'm thinking either Monday or Wednesday.
Okay, I could also do it. Oh, you have a prior engagement. They have capstone though at U of A. So that's not gonna work. The other option is I don't teach in the mornings. Are you available in the mornings?
On Tuesday.
Tuesday mornings? You want to do it Tuesday morning? U of A people, can anyone log in on Tuesday morning? Because I know that room B312 is not used on Tuesdays. Sol has a class Sunday night. Does anyone want to do it Sunday night?
Sunday night's good with me. I can do that.
Actually, I got church.
Got church.
I'm just kidding.
Well, no, I mean, I have church, but it's Sunday morning. I usually don't go to church in the evening, but,
I was just messing
oh, no, today is not a day to mess around.
around. Oh, sorry.
That's okay. Don't do that today.
Don't force him around, bro. Yeah, Sunday night would be good.
It's my whole person. Messing around.
Sunday night, going once, going twice.
Resounding success.
U of A people, please. All right, I'm getting a thumbs up. That works. And okay. What time do you want to do it Sunday? I'm probably asking too many questions. You want Sunday evening?
Sure. 6:30.
6:30 Sunday?
Yep.
Sure.
Okay. I need to be quiet for a moment and email myself today's group work. Because
So, from scratch. Yeah. This is so good. Good, didn't you? that's Caesar's dressing. You put something else in there.
There's no basil, Caesar.
But
Oh,
there's
it's pine nuts too. So,
chilies, anchovies. Olive oil, leaves, basil. Pine nuts, salt, pepper. Cheese. And cheese, parmesan. Or pepper. Pepper.
Okay, I'm gonna share my screen with you. And I'll blow it up a bit. Here it goes. So I'll open a Dropbox for this. You can work on an individual piece of paper or you can take a screenshot of it. Right, and so this is where we left off last week. We do have a quiz today on 1.8. And then, as I said, we have a take home, or not take home, sample exam that'll also count for group work. Okay, so the in-person exam will be Thursday during class. So y'all don't need to log in Thursday during class. Okay, the review session. Did I give that to you last week?
Yes.
I'm so confused. All right, I revised it actually. I couldn't figure out why I had a half dozen copies of it.
You added prismatic segments.
I added prismatic segments, yes. I added 2.4, which is what we're gonna do today, which I will be honest is not straightforward. So we might want to not have that on. And I added thermal misfits. Misfits is the wrong word. Yeah, no, misfits is the right word. Yeah, the temperature change and misfits, I added just 2.5. And that might also not be, we might not want to go ahead and do that for the exam. All right, let me know if you have a screenshot. I'll put you in a breakout room so you can chat with each other. Give me a 5. All right. And yes, the in-person exam will be Thursday. And we will talk about that before close of class today on how that's gonna work. Why are we shaking? It's okay.
it's all the different variables for the same thing. For force in the book, the summation for prismatics was like L. Is or N L for force.
Sorry.
It's okay. It's not your fault.
And I'm gonna send you away to breakout rooms. So you need to unmute and talk to each other.
So if it's compression.
And then I'll bring you back. We'll go over this problem together. Let's do it this way. All right, you're off.
First section, go on.
Um,
From like point to like where BC inter like matches. Section B and C matches, but we don't include B. Point C, I suppose.
plus the length, just doing the same thing, same section. I think so.
Forces, I thought for the first part, don't you just sum forces for total? Section C.
Versions and then- Oh, for the first one, you sum the forces?
I think so,
Okay.
like 1,200.
Sorry, I forgot to open the rooms. I'm really not doing well today.
It's
Yeah, okay,
So like
okay,
maybe-
you're right, you're right.
something like that, I think.
So it'd be like negative 1,300 pounds plus 1,200
Something like that.
times the 36.
1,200 minus 13 times 36. At least that's what I got.
You keep your signs, like, if
If it's going
compression,
this way, it's positive.
It's tension, it's positive.
I think it's like since this is at the wall, you set it up so that like the wall is the X and Y origin. So P four is positive, P3 is negative, so therefore you get a compressive force that also has a result.
Oh, yeah, 12 is the positive.
Right.
Okay, you're right.
So you get an overall distance because it is compressive.
Yeah, no, okay, yeah, I'm good, cool.
Sorry, what again?
Negative 0.0085.
Yeah. Or 8.654 times 10. From B to C, there is a 100
There's
pound.
that left. It's from previous section. So
Sum it all up, right?
it's kind of like the factors.
Yeah.
I did a review a little bit ago, you've got some competition.
Well, Kate was asking me about a problem on the exam and what I like. What I thought I got. And
Yeah.
we, like compared notes and he kept getting an answer and I went back to my calculator and I put a multiplication instead of an addition on accident. So I definitely got that problem wrong.
Well, but I grade your work, not your final calculator answer, right?
Yeah, but it's still shameful.
It's shameful.
It's a personal thing.
Yeah.
That's okay, as I said today,
Shear stress.
Yeah, it was the sheer stress.
So the shear stress one, was that supposed to equal 0?
For which problem?
I've got people that haven't taken it.
Sorry. Actually equals 2.
That's still open.
Which one? Section. There, it's only gonna be pulling P1, so it should be. Cause, so you're like that, right, so this overcomes, cause this is section B, right?
Mhm.
So B has a tension pull plus. Cause this is here, right? On this side of
Yeah,
the bar.
this is
And this
here.
one is pushing from this side of the
Right.
bar. So this 1700's over here for this section, but there's nothing pushing back on it, cause this. I think,
1600 plus.
well, I just missed it, hold on. Would you get?
0.03.
Okay.
Oh, wow.
But empty, now that you're here, it's not so.
class.
Point oh three three. I don't know, that's a lot, there's a difference there.
Get ready to review.
Just worked it all together, just assuming every step that happened.
That one, if I was 17. What?
I added on to the templates.
Thank you.
And then so that's the remainder. There's, So
It's still going in the opposite direction.
no, there's 100 pounds. No, it should be. Right, because,
So this one's plus 100
so this one's minus.
and the last one's plus 100.
Alright, I think we're all back. Please, say hello in the chat. And we'll start working on this problem. I am really struggling today, so you guys are gonna have to help me out and maybe get a lot of extra credit.
We'll
By
see.
the way, I'm glad it kept you in your breakout rooms because I accidentally threw myself out of the meeting.
Did you guys come to a conclusion about our little quarrel there? What's correct?
Alright. So we ready to try this one?
So.
Okay, so what's going on here is we have a prismatic bar. And things are changing over the course of our prismatic bar, correct?
Correct.
We're given our three lengths. So we have a non-working pen. 60, this one is 24, and this one is 36. I think that should be green. And it should have a much smaller thickness. All right, so we're given the modulus of elasticity as E. Why is it E and not G?
Because it's. Right?
Because it what? Yeah, you were right, say it louder.
Because it's axial.
Because it's axial, it is not a shear force, right? And we also don't have any, well, I guess that doesn't matter. I was gonna say we don't have any wiggle room with this. So we have a wall on one side here at A, and then we have these forces coming in, and they are coming in at B, C, and D. So let's go ahead and cut this up, right? I'm gonna start by cutting it just short of C. So that's going to give me P3, which is coming in at 1,300 pounds. All right, by the way, yes, this was a question yesterday. If it's pounds, do we multiply by
No.
G?
No.
Do we divide by G?
No.
Okay, don't ask that a question when you're taking the exam. It made me grouchy. All right, and we know that this distance is 36. So let's go ahead and figure out our first delta. So our delta then is going to be, and that's over EA. So we're going to have 36 times my 1,300 divided by my elasticity. And let's double check units. What were those numbers given in? Oh, they're given in inches. We're cool. Okay. And what else goes on the bottom? Oh, the area.
Just 0.4 inches squared.
Okay, thank you. I didn't see the number. All right, so what ends up being my delta then?
Why isn't the P2 acting on that one.
Cause I cut it right before the P2. Like just a hair's width before the P2.
Did it all.
Uh-oh.
Great, great.
Okay, so. Pounds is a force. Excellent, Ellie. What answer do you get when you put this into a calculator?
And then with the 1,300 pounds being negative, since it's compressive,
Yes. So this does need to be negative. I've got some calculators running in the classroom. Ellie said she got negatives 0.01125.
Yes.
We believe Ellie. All right, and that's in inches. So I don't know if you heard Kate's question or not. He said, why aren't you including P2? Because I am cutting it a hair width away from P2. Oh, Ellie says she's in her redemption arc. All right. So now let's look at what's going on from from B. Does that make sense? We're gonna have to have P2 and P3, and that's going to be from, okay, so now we're cutting it. We aren't gonna see the P1. All right, so our first cut was here. Our second cut is like right there. It's before it sees the P1. All right, so if it's before it sees the P1,
She's got P2.
we're gonna have P2 and we're gonna have P3 and we're gonna have to add B and C together. I don't know who screwed this up, but all right. So we draw this out and do we change? No, we're not changing our diameter. All right, so I have 1,300 here, right? And then I have, well, hang on. We're just looking at the B part. But B is still seeing what's coming in from the other segment. So we're gonna have 1,300 here, and then this one is then going to be P2, which is 1,200, right?
Correct.
So my total force on this is then going to be 1,200 minus 1,300. So that's then going to be negative 100.
We add the length of.
We're only looking at the B segment.
So you do the 24 inches.
You're gonna do the 24 inches. All right. There was some mental math there. That always makes me nervous. So my delta is then going to be 24 negative 100 divided by 10.4 times 10 to the 6th times 0.4. And what comes out when we do that?
Forget the 24.
oh, yeah.
Negative 5.769 times 10 to the negative 4th, question mark?
No question mark, that's good.
That's good?
I got it.
Alright,
I want you guys, I got it.
So it's to the negative 4th.
correct. Negative 5.769 times 10 to the negative 4th. 6.
Jesus.
Oh, I rounded it up.
Sorry.
Good.
But do I have this right? 10 to the negative 4th, 1, 2, 3, 4, yeah, okay.
Yeah.
All right. Okay, now we can do the last one. So let's see what the last one is seeing. This is then gonna be the 60 inches, but remember, it's seeing all the forces that come before it. And it's still blue. All right, so it's going to see P1, which is 1700. All right, so we're gonna see 1700. It is then going to see 1200, and it's also going to see 1300. All right, so if we have then 1700 plus 1200 minus 1300, I'm thinking it's 1600.
That's.
So let's go ahead and find our delta. Our delta is then gonna be 60 times 1600 divided by, got the E, 10.4 times 10 to the negative 6 times 0.4. $0.02308 is what Ellie's saying online.
Correct.
Simon agrees. All right, so let's go ahead then and add these guys up. We're now going to sum our deltas, but you say they're calling it L in the book?
In the book, they had it as the
And that's
summation as n sub I.
Oh, yeah.
N sub I times L sub I over E sub I times A sub I.
The equation you're doing,
Okay.
but it comes out to be just delta.
Okay, so let's see, we're gonna have 0.00125.
Negative.
That one's negative, yes. Then we're gonna have negative 0.0057. And then we're gonna have positive 0.0238. When we add these up, then we're gonna get our final answer, believe it's 0.01125. Something close to that.
Your answer for the third section it should be 0.02307 or 0.02308, not
Okay.
0.0238.
Zero point zero one one two seven three one.
So what do you come up with then?
0.01127.
Oh yeah, that's right. Okay, now, is this gonna be an elongation or is it going to be a shortening?
Shortening. Elongation.
Elongation.
Gonna be an elongation. Why?
It's positive.
It's positive.
It's positive. It's just that.
What don't you get?
I was just saying, like, can you shorthand, just look at the forces? The
Have an
summation of
expectation.
just the forces to determine whether or not it would be an elongation or a shortening?
There's more going positive X than there is negative.
There's more force in the positive direction than.
Yeah, but it also depends on the length of the segment. Okay,
It could be
the
something.
bottom part isn't changing, but if we had, these forces are gonna add up to be positive, but let's say C is at 36, let's say C is 300.
That makes sense. If like the modulus changes, then it could, okay.
Yeah, if those lengths are changing, then I'm concerned we'll have an issue. All right, How are we feeling about these problems? That didn't go smoothly as I thought it would, but how are we feeling about these problems?
Feeling better.
Feeling better.
Just gotta get down the first cuts.
Yeah.
All right. So I believe we talked about the non-uniform conditions, correct? And these are all actually loaded. I wanted to do an example where we change,
Diameters.
yeah, well, diameters,
We did not do one of those, no.
no.
Or change diameters, we did. Last week.
Did we do one with a different diameter?
Yeah.
Okay,
The example we did last week in class was.
so we did do one last week that had a different diameter involved.
Yeah.
Okay, cool. I just wanted to make sure of that. Okay. So we started talking about how we deal with when things are not uniform. And I will be honest, this is the part that I think is the hardest part of the class. All right. So we're gonna start in on this. My guess, and I could be wrong, we might get through this and Simon goes, or Simon and Ellie go, oh, this is a joke.
They're not.
They better not. And therefore you can go ahead and put it on the exam. But let's look at this problem. Now I don't know what's going on with my lecture notes. Oh, I see what happened. All right, so we're gonna start talking about when it's statically indeterminate. Okay, and how we need to approach that. 2.5 thermal effects and misfits. That's, I think that's a little easier section to deal with, all right? But we have to get rather creative when it's statically indeterminate. Right, by the way, cartoon du jour. Because we all need a laugh. Here we go. All right. When I went to my little old lady boot camp class this morning, she really worked us out hard on Tuesday, and I can assure you the smell of Bengay was very strong with that one. Okay, so we're gonna look at a problem and then we're gonna talk about what the issue is. Not that problem, we just did that one. But if we look at this problem here, fixed end bar, 3 prismatic segments. The end segments have the following cross-sectional area and length middle, blah, 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 PB and PC are equal. All right, now we're gonna determine the reactions at the fixed support and then the compressive axial force in the middle. How is this different? If you just look at the picture, how is this different than everything that we've done to date?
There's 2 fixed positions.
There are 2 fixed positions. Okay, so now we have 2 fixed sides, and because of that, we're gonna have to treat things a little bit differently. All right. Okay. So when things are statically indeterminate, what is going on here? And let's just take a little tiny step back. If you think about statics as the class, okay, what do you do in statics? Well, you do your free body diagram. Right, and then you have your equilibrium equations. Right. So that type of information, right, is then not gonna be sufficient. We use it, but it really doesn't tell us about our internal reaction forces. And when I say internal reaction forces back in statics, we'd cut it. We'd bring up the wrong slide. And when you guys get to chapter, what chapter is that in? 7? You just took the class.
That 7 sounds good to me, somewhere in late class.
It's in late in class, yes. You know, we did this type of analysis, but really that type of analysis is shortchanging us on what's really going on. All right. So statics is basically not enough. And instead, what we're going to need to do to figure out these internal reactions is we're going to have to combine our statics with our deformation information. Was pretty easy on the last one, right? Because what was happening? It was just sort of hanging out there. But now we have an issue that it's no longer hanging out there, right? We now have walls on both sides. Okay, so if it deforms too much, what do you think is going to happen?
It's gonna collapse. Yeah, it's gonna pull the walls together
It's gonna, well, or it's going to bend,
for a bit.
but it's gonna fail, correct? So the way we're gonna handle this is we're gonna remove a wall, for lack of a better term. We're gonna then do what we just did, okay? And then we're gonna then use that, and we're gonna use superposition to put the wall back. All right? So that's big picture of how we're handling this. Okay, and I only have one example of this, which is really stupid of me because I think this is the worst, well, it is the worst part. I'll pull another example up. Okay, so first thing is we want to determine the reaction force at RA and RD. So let's review how we find reaction forces. Right, so we are just literally going to add those forces together in order to be able to create the reaction forces. So if we're gonna do this with, let me grab the picture. We're gonna do this, and we're going to start it by dealing with it in terms, if it's just, I shouldn't say just, if it's a statics problem. And find our reaction forces. Whenever I see that notification, the meeting's being transcribed, that always makes me nervous, because I'm like, wonder what it thinks I'm saying. AI does not always rock. Correct?
Correct.
Who found that out the hard way, Simon?
I don't know, who did it?
You did.
Did I?
Yeah.
Okay.
Did you get a lecture in statics that was not statics?
I suppose that's right, isn't it? I was not a part of that, so that's why I don't remember it, but
You were not a part of it? Yeah, you were.
I don't think I used it, no.
You weren't there that day?
I was there that day, but I didn't.
No, you didn't use it. The instructor used it.
Oh yeah, no, okay, yeah, that's for sure. Yeah, that was pretty bad. I'll
Okay.
say about that later.
All right. Actually, let's just take a little step back and talk about this for a moment. If because that one's a little complicated. I have a wall and I have a beam and I have a wall on the other side, can we then get our two reaction forces? And let's say there's a point in here, okay, and we will call it, I don't know, 100 newtons. We'll just do 100 newtons. All right. How would I then determine my reaction forces? This is a statics review. IT can be impressive, it's just sometimes it doesn't understand. It's a long, bizarre story. All right. Okay, so I've got this force in here acting axially. Then we are going to have reaction forces, aren't we? So we're going to have an axial reaction force. Let's call this A. Right? And we're going to have a reaction force here. And we will call that one B. All right. So if we are looking at this, really, how many equations do we have? We only have one equation. We have no forces in the y direction, correct? So we can only sum in the x direction. So what happens if we sum in the x direction? Right? We're setting it equal to 0 because we're back in statics. RA is going to be positive. P is going to be positive. And RB is going to be negative, isn't it? All right, so we need to find another equation. How do we then find another equation when we are in statics? How do we find, what other equation do we then use?
We'd use a moment.
We'd use a moment. Can we do a moment on this? Declan, can I take a moment on this diagram?
I don't think so, because
No.
everything's in line.
Right, we don't have a perpendicular force. So moments, which you will learn about next week, only come about when there is a perpendicular force. So we are going to instead look at this, and it's called the flexibility of force model. But we're saying we need another equation to be able to figure this out. So what we're going to go ahead and do in order to figure that other equation out is we're going to release the structure, right?
Let's do it.
So if I'm releasing the structure, this was the problem we were just doing, right? We will still have a wall here, but I'm going to take a wall out. And let's say the length from here to here, I need to be consistent with my notes today because I am struggling. This is going to be A, and from here to here, this is going to be B. This is still my force, P. Where is the deformation going to occur?
In section.
Okay, well, but the total deformation, it's going to expand which way? Right? The force is going this way, the force is positive. This is going to push out like this, isn't it? We agree? Right? If this is going to expand, it's going to push out this direction. All right, that actually gives us our second equation. Because what we've been doing is we've been saying, and I don't know how to make this go back to what it was. The total deformation, and that line is too thick. Math people, they screw everything up. All right, the total deformation is gonna be what? That's gonna be the deformation from A plus the deformation from B. So if I release the structure, and by the way, this is where this then becomes handy, right? We know how to calculate delta. We just did it in our group work, didn't we?
Correct.
Right? So what is it?
Oh, it's,
Over EA.
There it is.
PL over EA. All right. If this thing is not released and smashed between two walls, is it physically going to deform? No. Right? Okay, so that means what? That means that this total has to equal 0. If I use this equation here, we're gonna have what happening? We're gonna have our reaction force of A happening here, aren't we? Right, so if we look at that in terms of our reaction forces, right? This one is then going to be little a P over EA. This one is gonna go the other direction, and it's going to be B R sub A over EA equals 0. Okay, so this is why it's called the flexibility. It's negative because of the way the RA is pointing. Right, and so that's why it's called, as I said, the flexibility equation. So here is the thing, I told you P was 1,000. If I give you A and B, can you now solve for RA? Sure, in fact, let's do it, okay? I said P was 100, right?
Correct.
Let's say A is, I don't know, we'll call it 30. Let's say B is 60. All right, and we need a E and a little a, so we'll just use the numbers from the previous example. 10.4 times 10 to the negative 6, positive 6. No. It was positive 6?
Yes.
It must be in PSI. Oh, okay, never mind.
The area was 0.4.
And the area was then 0.4, and that's in inches squared. All right, so what is this going to do then, right? I know my A is 30 inches. I know my P is 100, right? Over my EA. Times 0.4 minus B is 60. Right? Don't know what RA is. That's what we're solving for. You know what? Since this equals 0, it didn't really matter what the numbers are on the bottom. That's okay. I just made a mistake. What mistake did I just make?
Oh.
That's
I didn't know what that
What'd you say?
nothing. I was like, oh, like I know what that means when you erased it.
So it's the total.
Yeah, RA is acting on the total length. All right, so can you figure figure out, RA is, then going to be, 30 times 100 divided by 90. Did you guys all see? Simon said he saw, Kate said you're crazy. RA is acting, will be acting on the total length. P is only acting at 30. So because of that, I needed to add those two numbers together. That's where the 90 came from. It's the total length.
And you can arbitrarily pick that point of where you're cutting it.
So this P is only acting on this side, so to speak.
Okay.
Okay. RA is seeing all of it. So you don't arbitrarily, you typically pick the point where the force is given.
Okay.
Okay, does that make sense?
Yeah.
Okay, because that P, and we actually haven't talked about this or seen this before, this P is internal. So it's experiencing an internal force here. All right, did you run the calculator for me, Simon?
I got 33.34 newtons.
It can't be in newtons. Let's run it in pounds. I might have put that as 100, but if the bottom is in PSI and we're running everything else in inches, then let's make this 100 pounds.
Okay.
Okay, all right. Now, let's go back to our statics problem. Okay,
On RB now.
exactly,
Oh, look at that.
all right? Because what did we know if we took, well, we've got the wall here. We've got the beam. Now we have the wall here. Right? And this is, I think I changed units on you. This is P equals 100. All right? So if I draw this as a free body diagram, if I draw this as a free body diagram, what's going on here, right? We have P here, we have RB here, and we have RA here. This P is 100. So that means now what do we have? We have RB plus 100 minus 33.34 equals 0. That makes sense. Okay, I'm sorry, my brain had to take a moment and think about it. What does RB equal? These are probably because I put in bad numbers, but what does RB then have to equal?
133.34. Well, so in the.
No, it's subtracting.
No, but in the first way that you drew it, RA is on the left side, pointing in.
I agree with.
Oh.
actually.
I flipped this around.
Yeah.
RA. Sorry about that. RB, should just give everyone extra credit today.
But then it wouldn't be 33 anymore, would it?
It would still be 33,
It'd still
but
be
it'd be
33.
RA
RB
plus 100 minus RB,
Yeah.
and then you bring RB over. That would be 133.34.
And I was worried about the negative, which actually fixes it. So, does it? RA plus 100.
Minus.
RB equals 0. We found RA though.
Oh, we found RA.
Yeah.
Did we?
We had found.
Well, in the example, you put it as RA.
Stay calm. Okay, so RA, RB. RA plus P minus RB. We took away a wall. So
We took our.
we actually took RB away.
Solves for RA and.
We
the
solved-
Final.
For RB. Because that one's pushing.
So our RA is 33.34 pounds. So then it would be
Oh, I see.
the 100 plus 33.34 minus RB.
E equals 0. So RB is then going to be 133.34 pounds. All right, so in statics, we did what? We took moments in order to be able to solve stuff. Now we're like, well, we don't have a moment. So we're gonna have to do things a little differently. And because of that, we're gonna use these statically indeterminate structures, okay? And basically, we do what we just did, except we remove one wall in order to be able to get an answer. Let's do another one. Should we do another one?
Yes, please.
Oh, we can go back and do 2.412, because that one is prepped. Do we need a break? Actually, I need a break.
Yeah.
All right, so when we come back, we will then do this problem. So you guys get your 10-minute break. When we come back, we will do this problem and see if we want to do a third one on top of that. My guess is we should probably do the problem out of the sample exam that I gave you. Or we can do a different one, 2.49. We could do that one.
Any problems, a problem with me.
Okay.
They're all
Gonna
problems.
be,
Yeah.
gonna be on the exam.
No, one of your homework problems will be on the exam.
Okay, okay. Let's do the poll.
All right, so Zoomers, feel free to take a 10-minute break.
So I hate to keep asking, but is there any update on that?
No, I can try to call tomorrow.
Alright,
I'm gonna have to call and force someone to walk me through it.
yeah, I've been putting off buying a physical textbook because
Right.
I'm waiting for the,
Online version?
yeah,
I will call tomorrow.
well, thank you.
We probably got the other three wrong. Okay.
Well, that's why you're,
Stop talking about the fluency exam.
I think the lowest you can get is like what, a 25?
How much was your name worth?
nothing, a point.
Alright, folks, so. Let's go ahead and start this. Hello in the chat. Tell me you're back. Probably need to start drinking real tea and not the herbal stuff. I just realized. Ellie's back. Is it just Ellie and the lads in the classroom? Oh, good. Brock is there. Amelia. Brock, you didn't have to go to Lavender Mine or Copper Queen or something. I don't know where they are. Oh, good. I don't know if that's good or not. There apparently was a car that crashed into the Lavender Mine, like in the last week or two. All right. So this one's a little more complicated, right? We have a fixed in bar ABC. D consists of 3 prismatic segments. All right, so that word gets Kate all excited because he gets to figure out where to cut it.
Yeah.
The segments have cross-sectional area and length. So we've got a little bit more happening now. We have a different cross-sectional area and we have different lengths. All right, we also have the loads PB and PC. All right, and those are equal to 25.5 and 17 kilonewtons. So we want to determine RA and RD at the fixed supports. So we look at this problem and we go, oh yeah, this is just a statics problem, no issues, right? The response in the classroom was sure. All right, I want to make sure I already did grab it, okay. And because I did that other example, let's make things more readable. There we go, put that there. Then the lecture notes will actually flow for the people who are off on the field trip. All right, so let's go ahead then and put this together. So I approach this and I say, I'm a static student, I can do this. All right, so we start off, we have A, we have our section B, we have our section C, right? And then we have our walls. So this is PB. This is then my PB force. And this here is PC force. There are 2 reaction forces on the edges, right? I always draw reaction forces as going in, but we're going to end up with a negative answer, and that's okay. So we have a reaction force RA, and we have a reaction force here at RD. Right. Knowing the fact that we have all been successful in statics, what are we going to do? We're going to sum our forces in the x direction. Guess let's just go with it. So that means we're going to have RA plus PB minus PC minus RD. That's all going to equal 0. We are given PB and PC, I believe. Yeah, so PB is 25.5 and PC is 17. So we're going to have RA plus 25.5 minus 17.0 minus RD equals 0. Right. So that means we're gonna end up with RA minus RD is then gonna be what, -8 and something? 0.5? Did I do that right? No, I didn't do it right. It's gotta be 7?
Good.
No, it's good, okay. All right. We have a problem. That's our only equation. Can't take a moment. We have no equation in the y direction because we have no forces in the y direction. All right? But we are no longer statics majors. We're much more sophisticated than that. We are solids majors. So what else do we know about this?
Our deltas.
Okay, so our delta AD, which would be then the deformation of the entire bar. All right, that's then going to be the deformation of each of the segments. So we're going to have delta AB, BC, and CD. But we're between two walls. So can this bar really expand out?
Yeah.
Negative. All right, so this is then going to equal 0, correct?
Correct.
All right, so we go, well, that's all wonderful and delightful. But how can we then go in and deal with this? Well, we're going to, oh, I guess we can just leave it like this, can't we? Because we went in and removed a wall. Or we could do it this way with 2 equations and 2 unknowns. Which way do you want to do it?
Can
I
we
see it
keep
falling out of the way.
consistent?
What?
Can we do it the same way we did it the first time?
Sure. All right, which wall are we going to leave alone?
Let's do A.
We're going to leave A alone. All right. So these are going to be our 2 equations. All right, and the decision was made to leave A alone. So for leaving A alone, let's go ahead and put this on this sheet. So we're going to remove the wall at D. All right, if we remove the wall at D, that looks fuzzy to me. Make it a little smaller. We remove the wall at D. Let's see what we have left. All right, so we're still going to have the wall at A. Okay. We are then going to have this segment here, right? And we then are going to have this bigger segment. So now we are changing length and diameter. If I'm changing length and diameter, what is that going to affect? Okay, it'll affect the delta. How will it affect the delta?
Cross-sectional area would be different.
The cross-sectional area is going to be different for each segment.
I have a question.
Cancel out the bottoms.
We can't cancel out the bottom on this one. No. All right.
Dr.
and-
Monique, I have a question.
Yeah,
Can you hear me?
yeah.
Why are we removing the wall?
We're removing the wall because if we remove the wall, we can then figure out what the delta, we can then use the delta information to figure out what RD is.
Okay.
Okay, so if we go back one, right? If I want to find these reaction forces, that's what it said, determine reaction forces. Did you get a picture of this? Russell, I think you're talking.
Yes, yes, I got the picture.
Okay, you got this picture. So if I just go back and I do statics, I'm gonna be screwed up, aren't I? Because I have,
Yeah,
that's
because we
fine,
have two
Jose.
unknowns.
I have one equation, I have two unknowns. So
Yes.
we're gonna bring a second equation into play. The second
Which is the
equation
delta.
we're bringing into play is the fact that there is going to be, it's going to have a delta from that axial force, right, along all three of these.
Okay, and then we can pick which wall we choose. Is it gonna matter if we pick the other side, or it's not gonna make any
No,
difference?
it's not gonna matter, it just allows it allows it then, by doing this, we're getting rid of the RA force, basically. So we can figure out what RD has to be.
And if we pick a different wall, would our problem make it easier, like how we used to do a moment?
No, it's not gonna make any difference.
Okay, thank you.
The walls behave the same.
All right.
Okay. So let's go ahead and figure this out. I guess we will start from, I guess it makes sense to start from RG. Right, so we know in general, delta is going to be PL over EA. Oh, and by the way, if this is varying in here, we could set this up as an integral, couldn't we? Like if the area was changing as we move along the length, we could set it up as an integral. I don't believe you have any of those problems, but just as an FYI. All right, so let's go ahead and look at our first segment. This is acting here, right? PC is acting that direction on C. So my quote unquote cut, right, is going to be just this side. So my delta, we'll call it delta DC. All right. That is going to then be RD because of what it's seeing. The length of that segment is L1. Oh, I lost the problem. So the length of that segment is L1, which is 200 millimeters.
So
L1, L2, L1.
I'm sorry.
No, you're fine. You're fine. You're keeping me straight. Making sure I'm doing what I'm supposed to be doing. So L1 is 200 millimeters. A1 is 800 millimeters squared. Are we given E?
No.
Okay. So we're just gonna let E float around the equations. Actually, it won't matter because E is gonna be the same. We're gonna assume E is the same and then it's gonna disappear for us, isn't it?
Yep.
And then the A for A1 is then given to us as 840 millimeters. You guys giving each other grief? All right, let's now look at the BC segment, but we're gonna cut it so it doesn't see PB, right? All right, now, the forces we're gonna see is we're going to see RD plus BC. PC is, that was given to us, was that the 17th?
That's it.
Okay. All right, then we've got the BC length, which is 250 and 1260 are the two numbers we're going to be dealing with. All right, our final one then is then going to be AB. So AB, oh, this is negative. And this is negative. Right? And PC is negative. All right, PB is going that way, correct? So that one is positive. So then we're gonna have 25 minus 17 minus RD. And then that's going to then be, we're back to the 200, aren't we? Yeah. 200 over E times 840. All right, these all have to add up to equal what? They're gonna have to add up to equal 0. So we're gonna have RD, by the way, put in 200 divided by 840 for me.
0.238.
Divided by E. All right. Then 250 divided by 1260.
0.1984.
All right, divided then by E. 17 times 250 divided by 1260.
Which one, sorry?
17 times your 1.98.
17 times 1.98 is 3.373.
All right, last one. Right, 200 divided by 480.
You mean 840?
I mean 840, yes.
It's 2.023 or 24.
2.04.
2.02.
Try it again. Point.
2.024.
2.024. That doesn't make any sense to me. 200 divided by 800.
Well, yeah, and then you multiply your 5.
Oh, you're doing the 25. I was doing the RD.
Oh.
Okay, we're not communicating. All right, so times the 25, that's a plus now, 2.024 divided by E. All right, now that times the 17.
Hold on, I think disregard all my numbers. I'm doing it totally different. Because I'm calculating each delta individually. And then you're gonna add them all together.
$200 divided by 840 is what?
That's 0.238.
Okay, that one's fine. 250 divided by 1260
That's 0.198.
times 17.
3.373.
Okay, so we're good. So 25 times 200 divided by 840.
It's 5.95.
All right. So this is where we went south. So this one, oh, did you subtract them first?
Yeah.
Oh, okay. So 25 minus 17 is the 8.5. That's where the other number came from?
I believe so.
All right, so 25 minus 17 times 200 divided by 840.
That's 4.01. Negative 4.01. Oh, hold on.
No, it's gonna be positive.
Hold
Uh-oh, Simon's having calculator problems. Tyler's out.
Don't look.
on. Right,
What
it's
do you do?
1.904 or 905. Just calculate.
No, the links are not compounding. What is it?
1.905.
1.905 divided by E. Finally, 200 divided by 840.
That's 0.238.
Okay. Now, the reason I was sort of talking to myself, right, and I said, well, just run it with E because that has to equal 0. So since that has to equal 0, if we multiply through by the E goes away. All right. So we end up with what? Let's start here. Negative RD, please add 2.38 plus 2.38 plus 1.98.
So it's 238, 198.
Yeah.
6.674.
All right, 0.674. So to answer your question, Ellie, we're not adding them together because of the fact that we've got different areas. All right, then we need to take negative, that's going to be negative 3.373 added to 1.905.
She just did the alphabet.
It's gonna be negative 1.468.
Negative 1.468. Cool. What was the question?
Determine the reaction force.
No. There was a question over here.
Maybe I'm not good with calculators either.
Oh, okay.
Everything's falling apart over here.
Kate with me, I swear. No, I didn't get that. I got 2.456 for your RDs put together.
Your coefficient RD.
You added 238 twice?
Yeah, 238 twice plus 1.98.
You didn't get 0.647.
7.
0.6, you didn't get 0.674.
Plus
4.
So I'm looking at 238 and 238. That's going to give me 4.6. You guys are going to make me do mental math.
Dude,
So now I have 4.6.
is that not the same?
Yeah, because 1.98 is 0.198, my friend.
That makes sense.
Okay.
Oh my god.
They're on purposely causing mass confusion in here. 6.8 divided by negative 6.74. It's going to be negative. That's okay. All right. What's the answer?
So negative 2.178.
Thank you.
Is it over?
It's over, sort of.
Oh yeah, we still gotta figure out what,
But I'm very happy with that answer. The author did it a completely bizarre way and he got the same answer. All right. So we now know our RD is negative 2.178. It's negative. That does not freak me out. It just tells me what? I drew the diagram wrong. Okay? Right? Remember, in statics, if we get a negative force, it means we drew it wrong. So let's go back to our original diagram. Small segment. fat segment, skinny segment. I drew it as, and then this one,
Drew it as compressive.
I drew it as compressive. I should have drawn it in tension. So this is 2.178 kilonewtons. This one here, is this the 17?
Yes.
17. This one's 25.5. All right. I drew RA like that. It's gonna be, or no, I drew it the other way, didn't I? It's gonna be negative also. All right, so I drew RA as a compressive force. If you remember back in statics, when we ended up with a negative number, it means our free body diagram was wrong. Okay, so this is going to be RA plus 25.5 minus 17 plus 2.178 equals 0. We're back to summing our forces in the x direction. So that's going to be 8.5 plus 2.178. So it's basically going to be 10.6. Right? Did the calculator confirm that?
That's cool.
I'm giving up on the calculator tonight. We're just doing math in my head. 10 point, what did I say, 10.6?
Yep,
I guess it'd be 7.
6, 8, close enough.
Okay.
You sure?
Kilonewtons. Smack him. All right. So, and it's going to end up being negative, which means I freak out. No, it means I drew it wrong, correct? I drew it in compression. I should have drawn it in tension. So it should be going that way. All right, so how are we doing? I believe there was a part B to this problem. It's not a part B to that problem.
Determine the compressive axial force of BC in the middle segment of the bar.
Oh, well, heck. That's easy, isn't it? Or I should say it's easier. All right, so let me redraw this free body diagram the way it's supposed to look. We'll go back to blue and tell it we want it skinny. I need to figure out how to set that. All right, so this is what we have. We know this is going this way. What did we say it was? 10.68?
Wouldn't it be, we said it was in tension. wouldn't it?
Oh, you're right, it is in tension. This is in compression. All right, and this one was 25?
Yep.
This is in compression. It's a little short. This is in compression and it's 17. This is in tension and it was 2.178. All my units are kilonewtons. Now, when it wants to understand the axial force at the center of BC, right? That's what it asked for. What are we doing? We are back to statics. We are going to cut it. What did you say?
We were getting excited to sum the forces, but I guess not.
Well, no, we are going to actually sum the forces. All right. Because it doesn't matter which side we solve for, right? Cause yes, we're gonna sum the forces, we're just gonna do it with a cut in it. You've done this problem 100 times. So I wanna know what this axial force is. So that axial force is then going to be 10.68, that's negative, plus 25, so we're gonna end up with 14 and change. It's gonna be what, 32? What'd you get?
Yeah, that's right.
14.32. All right. What's cool? Well, I guess it depends on your definition of cool. If we look at it from the other side, this is 17. This is 2.178. So that's going to be negative 17 plus 2.178. We're going to be back to that 14 number, I hope. Oh, this is 25.5. So this is wrong. Now I'm not an eraser.
Well, comes out just fine.
Comes out just, I'm being told it comes out fine. Does anyone online agree? What does it come out to be?
14.82, so.
Perfect.
A2, you say?
Yeah. I do say.
I can't deal with this board. Let me put this down. I don't have a blue pen in the other room.
Yeah.
All right, so we ended up with what? 14.82.
82.
Right? One is positive, one is going to end up to be negative. Because if the axial force is going this way, the other axial force is going that way, correct?
Right.
Right? Which then is going to result in a compressive force. Yes, the answer is in kilonewtons. All right, so, which is, I don't know, I think that's kind of cool. It all fell out for us at least. All right. How are we doing with these problems? Can I put this on the exam?
You put just some.
This exact problem right here.
Okay.
I'm sorry, not supposed to mess with you today.
No, don't mess with me today. All right. Okay. So let's talk. I was going to give you a quiz. Let me introduce thermal misfits and thermal effects and what that does to the whole scenario. And then we will so at least look at some equations down and talk about how we're going to deal with thermal effects. All right. And we'll have to do misfits and pre-strains next week.
Not next.
Yeah, I know, but I don't even know. Well, let's go ahead and introduce it because then you'll have seen it twice. All right, so let's talk about what's going on with thermal effects. When you heat stuff up, it has a tendency to deform. Do we agree?
Yes.
All right, so we get a deformation when we're heating these bars up. All right, and that's going to cause, so you'll see this diagram, we have length and then we have delta T. And the delta T actually stands for temperature, and then we're going to get the big delta T is change in temperature, the little delta T is then that expansion that we're seeing. All right, so we heat stuff up and it expands. This is 2.5. Yeah. All right, so
It's restricted.
this is going to be epsilon sub T is then equal to alpha delta T. Let's break this down and what this is. Epsilon sub T, by the way, epsilon, that should look familiar. What is that? It's going to be strain. All right. In this case, it's going to be axial strain. We will get into things that are not axial. We'll get into radial stuff going on. All right. Alpha is the coefficient of thermal expansion. It-
Given,
It has to be, because it's going to be a material property. All right. All right. Your delta T is then going to be your temperature change. I just thought of a great pre-class quiz for you guys to do.
So. Would like just sign convention, we should say expansion is positive.
Yes. All right, they're frowning at the board. Those of you that are virtual, have you ever baked cookies? You start with a blob of dough. What happens when you put it in the oven?
Expand.
It's going to expand into cookie shape, correct?
Oh, but that's a different thing.
Yeah, that's different. All right. So what we'll do is you'll measure the diameter of your cookie dough blob. Then you will measure the diameter of your finished cookie. All right. And calculate what alpha has to be for your cookie dough.
cookies?
We're making cookies.
Yeah, a lot of cookies, guys.
All right. So, because you guys need something fun to do after your exam. The delta T is how much that's going to be changing, isn't it? So our delta T is basically, that's going to be, right? We've been doing this sort of all along. That's going to be strain times RL. We know that this is then going to be alpha delta T. You would assume L is some constant, it's just a long bar. You are basically, when you do your cookie, you're looking at the cross-sectional area. Actually, when we do radial expansion, that's probably when we should do the cookies. We can do it here too. All right, so these are our new equations that we're going to use. Now, we got to talk about delta T. All right, so in theory, so delta T, and I'm not sure if it's initial, you guys have the book open. Is it initial minus final or final minus initial?
Oh.
Did they spill it out for you? No,
Delta T not.
2.5, that's a fun chapter. Make sure you're here for it. They just call it delta T. All right, I guess that works.
This would be positive.
Yeah, well, I think it depends if we get expansion or contraction on whether or not it's gonna be positive. That's statistically determinate. Okay. Okay, so let's talk for a minute about delta T. When we talk about temperature, we typically want to work in units of either Kelvin, which Kelvin is associated with Celsius, or Rankine. Rankine is associated with Fahrenheit. Okay? Kelvin, to get from Celsius to Kelvin, you add what?
73.
Yeah, so to get to Kelvin, you add 273 plus the Celsius. I think it's 490 for Rankine. Someone Google it. The conversion between Fahrenheit and Rankine. It is, oh, I'm way off. Oh, no, I'm not. 459. I was close. The dyslexia got in the way. So to go to Rankine, it's 459 plus, and then it would be whatever your Fahrenheit is. Celsius and Rankine have the same theory behind them. That's absolute zero. Okay, absolute zero is when a crystal is perfect and it's at absolute zero, its entropy is zero. That is how that is calculated, right? Entropy is amount of disorder. Okay, so that's a little bit of thermal thrown in for color. All right, so therefore, if you are given, if I tell you that the change in temperature it's the delta T, if I give it to you as 50 degrees C, and that's the change in temperature is 50 degrees C, you don't need to convert it because you're just going to be adding 273 to the two numbers, right? So if it's a delta T is given, if delta T is given, just leave it alone. Treat it like it's unitless. All right. Okay, because if I'm adding 273, and you can look at it this way, if my delta T is equal to 50 degrees C, and my delta T went from 0 to 50 degrees C, what's happening? I'll add 273 to both of these. So it just is going to be 50 degrees in the end. Okay, so something to keep in mind, don't get caught up in, and I was trying to explain this to thermo, but they weren't listening. Don't get caught up in having to turn it into 273. I had a student in thermo last week that was arguing with me about that. That was like, no, I have to convert it to Kelvin. I'm like, then convert it. I don't care. You're going to get the same answer. That makes you happy, do it.
It's about the change, not about the actual.
It's about the change, not about the actual temperature. Okay. Alpha, we're going to treat alpha like it's a constant. That is a lie. All right. Alpha will change as the temperature changes, but we're going to treat it in this class like it's a constant. All right. So we have an aluminum pipe. It has a length of 60 meters. Right? An adjacent steel pipe at the same temperature is 5 millimeters longer than the aluminum pipe. What is the temperature in degrees Celsius will the aluminum pipe be 15 millimeters longer than the steel pipe? And then they give us the coefficients of thermal expansion. And this one is 240. I want to see what drawing they had in here. 2.52, so it's an easy one. That's okay.
248.
No drawing, I know, I'm looking at the solutions to see if there was a drawing in the solutions. And there it is, all right. So we want to figure out when the aluminum pipe is gonna, I'm thinking we might want to do something a little easier. When the aluminum pipe is 15 millimeters longer than the steel pipe. All right, so we have two adjacent pipes, right? We have our aluminum pipe and we have information on that aluminum pipe. And then we're going to have our steel pipe. Right? They're adjacent. It doesn't say anything about them being, for lack of a better term, them being welded together or anything. That would actually be a really cool problem. All right, so let's redraw this. Here is my steel pipe. In order to visualize it better, I'm going to draw it this way. All right, we have an aluminum pipe. I wanted that to be blue. Fine, we'll just be thick. We have an aluminum pipe. That is going to expand, correct? So it's going to expand some delta, and we'll call it delta A since it's aluminum. Right? We then have our steel pipe. When we heat up the steel pipe, what's the steel pipe going to do? It's going to stretch. So that's going to be my delta S. All right, both of them are going to have some stretching involved. All right, so we want the aluminum pipe. All right, so there's some temperature going on here, correct? Right, so we're going to have some delta T that is then causing this expansion. We want the aluminum pipe to be 15 millimeters longer than the steel pipe. All right, so to do that, what are we going to have? Well, we have the original aluminum pipe length. Plus, we have the change of the aluminum pipe length. Right? And we want the aluminum pipe be 15 longer than the steel pipe. So we're then going to have 15 plus the length of the steel plus the delta of the steel. All right, because we want the aluminum to be 15 longer. So in order for those to be equal, we have to add 15 to the steel. Kate's nodding his head, but I don't know what that means. All right, so now we can go in and we can plug in our information. And really what we're looking for is that delta T. So we have the length of the aluminum plus
I have a question.
alpha of the aluminum times the delta T times the length of the aluminum is then gonna be 15 plus length of the steel plus alpha of the steel, which is different than aluminum. And actually the iron, well, we're not gonna worry about the iron content. Delta T length of steel.
Dr. Monique, if we
Yeah.
want to make the aluminum longer, don't we have to add the 15 to the aluminum, not to the steel?
No, it says, will the what temperature the aluminum pipe be 15 millimeters longer? So if we are looking at it this way, let's rewrite this. If we are looking at it, final length of the aluminum is then going to have to equal 15 plus the steel. The steel is 15 short. And we gotta watch units because it's actually in millimeters. And everything else is given to us in meters. So it's really not gonna be 15. It's going to be, what was that gonna be, 0.015?
Yep.
All right, so we're looking at the final length of the aluminum and the final length of the steel. The aluminum is going to be longer than the steel, so for them to be equal to each other, we have to add that to the steel. We want to put this all in now and solve for our delta T. So our length of the aluminum pipe is given to us as 60 meters. So here's the aluminum information. Right, we're at 60 meters. The alpha of the aluminum pipe is 23 times 10 to the negative 6. The delta T is what we're solving for. All right, and then we're going to multiply that by 60 meters. So that's my aluminum information. That is then going to have to equal right, 0.015 plus the length of my steel is 5 millimeters longer. So they're basically the same size, 60.5 millimeters. That's gonna be what, 0.05?
Yes.
0.005. Right, divide by 1,000. All right. Okay, and then we are then gonna have, and this is the steel. All right, and my notes are gonna lose me points. This is then 12 times 10 to the negative 6 delta T. And then we're going to have times the length of the steel, 60.005. All right. Now, if you're at this point, can you solve for delta T?
Yes.
All right, I'm gonna write it down because I want to get the folks in the room their quiz. So delta T is then 30.31. All right, and we're gonna, it's the alpha numbers were given to us per degree Celsius. Oh, and we're given a starting temperature of 10 degrees. All right, so our delta T is going to end up being 30.31. All right, delta T, here's the answer to that question, is going to be T final minus T initial. So that means we're going to have 30.31 is then going to be T final minus 10. So my final temperature for this to happen is 40.31 degrees C. All right, I don't think these are that bad. When they get bad, well, actually that one's not going to be bad either, is when we put the walls in. Do we put walls in? No. It doesn't look like it. All right, we will do another problem similar to this in 2 weeks. If you are taking your exam virtually, we will not have class, so don't log in. Don't log in and then send my boss, who's the dean, an email telling them that I canceled class. I didn't cancel class. We're taking an exam that day.
Did you take care of the fluids attendance for the students? I received an.
I thought I did, but I will double check on that.
Okay.
Yeah. And I need to take attendance today. So hang on, folks. You guys want your quiz while I take attendance?
Sure, why not?
All right. Those of you that are virtual,
With enthusiasm, brother.
I'm gonna have to give you some equations, I think. Yeah, we're gonna have to give you some equations.
You know what the quiz is on? I'm very clear. 1.8.
If you've taken it online, you got screwed up because you're gonna need some equations for this. All right. All right, so let me give them their equations and then we will take attendance and then you are, well, I'm not gonna say the word because you'll leave.
So when is the exam?
Next week. When would you like it opened?
So it's gonna start from Thursday?
Yeah, Thursday at
Okay.
midnight.
All right.
All right. So here are the two equations you need. You need the fact that, I don't want to do it on there. Now average is, then going to be your P over BL, but watch that. Right, because it's gonna be P over your area. Watch what the P is, that's just a hint. And then the other one you're finding is gamma. So gamma is gonna be your tau over G. So I'll send out an announcement explaining, the review is Sunday night and explaining how the exam will be set up. If you are virtual, please hang on for just a moment so I can take attendance and get out of attendance jail. All right, Tyler, you're here. Simon is here. Gibran, are you online today? Ruel Perez. Are you online? Chat. Remove chat. There it is over there. All right, okay. Kate is here, Declan is here.
Dr. Minky, Raul Perez was here. He just left just before you started taking attendance.
Thank you. All right. Rasul, you're here. Mushen, I believe you are here. Michael, is Michael here? Thought I saw him earlier. All right, Austin. Melody, you're here. Ellie, you're here. Amelia, you're here. Jose left a little early, but he was here earlier. Brock, I know you're here. Robbie is not here. and Alex is not here. They're visiting that month. Okay, great. So your attendance is updated. I need to put into D2L your, the quiz is open. Please let me put in the equations you need, and then you'll be ready to take your virtual quiz. Next week, there will be no lecture because there will be an exam. If you would like to take the exam in person, you are always welcome. We are on the Northwest Campus, A106, and it will be from 3:45 till 6:30, but it won't take you that long. But it has to be harder than the fluids exam. I've already made that decision. All right, guys, have a wonderful evening.
Have
I
a
will
good
see you
evening,
Sunday
Dr.
night.
Mickey.
What?
Have a good evening.
All right, you two, I'll see y'all Sunday night.
Dr. Minkey, I actually had a question regarding dynamics.
Dynamics?
Yes.
Okay.
Just real quick, it said on the announcement that it was going to be open until tomorrow night, but currently it says for the actual assignment that it's due tonight. I just wanted clarity on whether or not it's due tonight or tomorrow night. For ENG230.
Yeah. Let me get. Let me get into that. If I said in the announcements it was tomorrow night, I'll push it out. I have 9/19/11/59. So yes, it is tomorrow night. I will go in and fix that right now.
Awesome. Thank you so much.
Yeah, take it sooner rather than later.
100% yes.
Okay.